And welcome back. As we dive into a new topic, today we're going to be looking at something a little bit more advanced. We're introducing a new data structure, and that is going to be the linked list. And to do that, we're actually going to take a step back and look at it through the perspective of with nodes. So nodes and links are very important things in Java here. A linked data structure is simply just what consists of capsule of data, which are known as nodes, which then are connected via what are known as links. Now, these links can be viewed as arrows and thought of as a one-way passage from one node to another. The simplest kind of linked list data structure consists of a single chain of nodes, and this is what's known as a linked list. And we have a quick visual here of what that linked list might look like. You can see we have a head followed by a series of lists here. You can see we have a string and we have a numeric value in here. And of course, there's an end marker here, which shows this is the end of that list. And it's a very simple linked list that we're looking at here. And these nodes are holding two kinds of data. As I already mentioned, we have a string type and we have an integer. This could be, like in this case, a shopping list that we could have here, but we could make it a linked list of just about anything. Now, the links themselves are depicted here as arrows, and you'll notice that when we traverse this, it can only go in one direction. You cannot go backwards here in this list. So we have a first node, a second node, and so on all the way to the last node. Now, the first node, this is very important to note, is what's known as a head node, and you can see our keyword head there. Now, when we start generalizing what a linked list is, we look at this example, it's a little vague as what is actually happening or what kind of coding we need to do with the linked list. Now, it becomes a lot clearer when we start looking at a linked list in some programming languages. In Java, the way this is handled, nodes are objects of a node class. The data in a node is then stored via instance variables. The links are then realized as references or a memory address. The reference then stores a variable of a class type. And the link, therefore, it would then be an instance variable of the type of the node class itself. Now, there is a linked list in the Java libraries. You can actually take a node and linked list and connect to the next nodes by having an instance variable of the node type contain a reference of where that next node is stored. And if you look in the java.util package, you'll actually see there's a linked list class. All right, and it works very well to use this class because it's well designed, well tested, save you a lot of work for what you need to do. However, if we simply just dump this in here and start using it, we're not going to get a good full understanding of how nodes actually work and how the link structure works. So we're actually going to look at our own kind of simple linked data structure. We can use the library version later on because we'll have a better understanding of how to implement it within our code. And so a linked list, as we mentioned, is a data structure. All right, we've looked at a couple of data structures already. We have arrays, we have array lists. Well, now we have linked lists. And then linked list is a single chain of nodes. Each is connected by a link. It's the simplest kind of linked data structure. Arrays and array lists aren't considered to be linked structures. They are data structures, but they're not linked data structures. However, the thing with linked lists is these are very widely used. They're a very common data structure that you're going to see. And a simple linked list is, as we already saw, we have nodes, which we are represented by boxes. And in Java, that node is going to be an object of some node class, as we're going to see with our node1 class. Now, each node has a place or multiple places for some data and a place to hold a link to another node. The links, as we saw, were shown as arrows and whatever node they're pointing to. In Java, those links, those arrows are going to be implemented again as references stored in an instance variable of the node type. Now, you might notice there's a little circularity things here going. The node1 class is defined by specifying, among other things, and it's a variable type 1, or node1, that is named link. This allows each node to store a reference to another node of the same type. So you notice it's talking back to itself here. It's almost like, feels like when we have recursion, it would a function call itself. There's a little bit of that circularity going on here, and it's perfectly allowed within Java for that node to be able to call another node here. Now, the head node of the list is our first node, or the start node, when we start looking at that data structure. Now, if you start at the head node, you can traverse the entire linked list, visiting each node exactly once. In Java, your code must intuitively follow those link arrows. We were following that path straight down. It's a one-way trip. In our diagram, the box labeled head, all right, that actually is not the head node. It's not even a node. The box label head is simply just a variable of type node 1 that contains a reference to the first node in the linked list. That is a reference to the head node. The function of the variable head is that it allows our code to find that first node. So it's a very important distinction here between like that, reference really and what the actual head node is. Now the variable head is declared very obviously. We just say like node 1 head, and then that's all we need. Now we start looking at the rest of the nodes in the list. You have to remember Java is going to look at this and say, hey, we got to make some sense of all these nodes that are in our list. And a linked list object does not directly contain all the nodes in a linked list. All right, it's very important to note this. It only is going to contain the instance variable head that contains a reference to either the first or the head node. However, every node that we have can then be reached from that first or head node. So it's a very important distinction here of how we actually handle this. The link instance variable, the first in every node 1 of the linked list, would then contain a reference to the next node 1 of that list. So again, that linked list object's not going to actually have in it. It's not like an array where you store everything inside of it. Now, each node object of a linked list contains its link instance variable reference to another object of the class node 1, and this object contains reference to another object class node 1, and so on and so forth until we reach the end of the list. And if you think about this, well, that means a linked list object indirectly contains all the nodes. It's just if you actually look at it, it's only going to physically contain one node because everything else is going to be a series of references. Now we start working with the linked list. The thing you have to remember is your code needs to be able to get to that first head node. All right, we have to get to that node. If we can't get to it, well, we're going to have some problems. And we also need to figure out some way to detect when we reach the end of that list, or what's that last node. So to get our code to the first node, well, we just use node 1, as we mentioned. That's always going to have a reference to that first node. And from that first or the head node, your code can then just follow the links all the way through the linked list. But how do we know when we reach that last node? What is the distinction for that to be able to work? Well, if we start looking at our diagram here, all right, we indicate the end of a linked list by setting the link instance variable of the last node to null. All right, and so pretty much we're saying, hey, it's a null reference. There's no more here. That way our code can test whether or not is the last node simply by saying, like, well, do you have your instance variable, is it null? Does it actually come back as such? And remember, when we test for null, we use equals equals. All right, we're not going to use the dot equals method like we do most things with equality. We're actually just going to use equals equals to see if it is null. Now, linked lists can be empty, all right, and we can use null, of course, to indicate an empty linked list. And in this case, the head instance variable contains a reference to the first node, or it'll either contain null if the linked list is empty. All right, so if we look at it and it's a head list as like we're pointing to null instead of pointing to the next node in the list, well, it's an empty list. The only constructor sets the head instance variable to null, and that indicates that newly created list is empty. Now, traversing a linked list is obviously the thing we really want to start looking at, because what good is to have all this data in a chain if we can't actually access it? So before we go on and adding how nodes are added or removed from a linked list, because obviously putting information or taking it out is going to be important, we need to discuss how the linked list already has, let's say, a few nodes, and we want to, for example, write all the contents of the screen. We want to print out that linked list. Well, we can do this with this method, output list, whose bias reproduce here. We have node 1 position goes head, while the position is not null. This is now print line, position.getItem, plus position.getCount, position equals position.getLinked. Of course, this is just going to get just the get item. This is getting the count, so we can help see what position it actually is in. And we're just updating that link there. Now, that position that we just saw is a local variable, and it's obviously just a reference to one node. The variable position starts out with the same reference as the head instance variable, so it starts out positioned at the first node. The position variable then has the position moved from one node to the next with the assignment position equals position.getLinked. So that little bit of code there is what is actually moving it to the next reference. And when we talk about moving position, we can see that the assignment therefore moves the position variable from the next node. And you'll note that the position variable contains a reference, all right, to the node pointed by the position arrow. So we always are looking at this reference of where are we going, what are we actually accessing. Position, of course, is a name for that node, and the position.link is the name for the link to the next node. So here's position.getLink. Now the value of link is produced with the accessor method getLink, and a reference to the next node is in the linked list as position.getLink. So again, just traversing this, using this, and of course when we get to the last node, you'll see that it's set now to null. All right, and when we want to move to the next item list, we simply just use position.getLink, and getLink will simply just look at the next reference and pull it in. Now, when we actually start talking about that last node, so once we get there, so the method output list continues to move along down the list, and outputs data in each node as it goes along. When it reaches that last node, it's going to output the data in the node, and then it's going to execute position equals position.getLink. However, you might have already noticed that at this point, our code is reaching the end. All right, you'll see it's like, hey, we're getting to the end. Oh, we're setting our value to null. Well, we want to stop that loop then. We don't want to keep going because we're null. So that's why we have position does not equal null. All right, a very similar technique is used to traverse the linked list. If we look at there's a size method and a find method, we can use the same thing. It's going to have the same kind of approach. Now we want to add a node because obviously adding data into our linked list is important. It's a method called add2start, which is going to add node to the start of the linked list so that the new node becomes the first node in the list. And we just do that with a single statement, head equals new node 1, and then item name, item count, and then comma head. And the new node is then created with the new node item name, item count, head, which is a reference to that new node. The assignment statement sets the variable head equal to a reference in this new node, making the new node the first node in the linked list. So it's very important to note that, it's not going anywhere in the linked list. Notice it's always the first node. So just something to keep in mind here as you start thinking about how to approach this implementation. And so when we update our reference here of how this works, so to link the new node to the rest of the list, we only have to set the link instance variable to the new node equal to a reference of the old first node. And in here, we've already done that. The head used to point to the old first node, so we just use the name head on the right-hand side of the operator, and the head will then denote a reference to the old first node. Therefore, the new node produced by new node then simply just points to the old first node, which is what we want it to do. So it's just updating this pointer. So it's instead of pointing here, it's now pointing here. Boom, easy peasy. Now, I want to remove a node. All right, we will discuss this a little bit later, but the easiest places to add node, of course, is at the start of the list. The easiest place to delete a node is also at the start of the list. Now, the method delete head node removes the first node from the linked list and removes the head instance variable pointing to the old second node in the linked list. All right, we just do head equals head.getLink because when we say getLink, that moves it down the list, boom, and it's now pointing to a new reference point. Now, obviously, with all this moving and adding and deleting and stuff like that, this could have a lot of garbage that gets generated. And so automatic garbage collection here is going to be really helpful. All right, taking the first node from the linked list leaves the linked list one node shorter. But, if you thought about it, we have this now node that's just kind of out there floating in space. So at some point, Java is going to say, you know what, you have this thing in memory, you're not using it, it's not referenced by anything, so it's going to automatically collect it along with any other nodes that are no longer accessible and recycle the memory they occupy. This is what's known as Java's automatic garbage collection. Now, we do also have to talk a little bit about some privacy restrictions here. If we look at the method getLink in the class node1, it returns a value of type node1 or a reference to node1. Now, in program 1, we had mentioned that if a method, such as getLink, returns a reference to instance variable of a mutable class type, then the prior restriction on the instance variable can easily be defeated, because getting a reference to an object may allow the program to change the private instance variable of the object. So that's why we looked at our instance variables and said, hey, we don't want these being private, we want, or public, we want these to be private. Instead, we use our accessor methods to go ahead and pull that data in. Now, obviously, there's several ways to fix this. The most straightforward of which is make, hey, say node1 a private inner class of the method node1. Now, there is no danger technically of privacy leaks with the class node1 when it is used within the class definition for linked list 1. However, there's no way to guarantee the class node1 will be used only in this way, unless we take some precautions such as making it a private inner class. Now, alternate solutions place both the classes into a package and then change the private restriction to a package restriction. Now, the privacy problem can technically arise in any situation whenever we have a method that's going to return a reference to a private instance variable. So we look at get item, and it comes very close to having this problem. However, in this case, the method get item doesn't actually cause a privacy leak, but only because if we think about we're using a string, and string is not a mutable class, and we don't have any methods that are going to change the value of the string without changing the reference. So if instead of storing the data type string in our list, we had stored data of some mutable class type, then defining access method similar to get item would produce that privacy leak. And just real quick, let's take a look at those classes. So here's our node1 class, and you can see we have our private instance variables right here. We have a string, an int, and our private node1. So we are, of course, creating a private version here. And here's our constructor. We have our other overloaded constructor here, and we have a set data. We have a set link, get item, get count, and get link. Pretty simple. And if we look at our linked list, then what we have here is our method. So here's our add to start method with our appropriate calls that we saw before. Here's the delete head node, allows us to remove the head node, and of course it returns true if there's at least one node. If it's false, the list is empty. Size will get us the number of nodes in that list. Contains is a good way to, of course, look for a particular thing. This is a node1 find, so it's looking for a target item and returns a reference to it. And of course, then we can also output the list. And if we look at our linked list demo here, you'll see we're creating a linked list here, and when we create it, it doesn't have anything in it until we add items to it. So we go ahead and add some items, and so I've added 3 items here. And then we're simply just going to say, hey, you know what, this list has how many nodes to it? So we're going to print out that size, and then we'll output the list, and we're going to look and say, hey, does it contain this item here? So we're going to look where it is, and then if we delete that list, what does that change to? And then, of course, if we look here, this while list is an empty loop body, all right, because we're simply just going to output it. And if we run this real quick, all right, you'll see that we have our list has 3 nodes, cantaloupe 3, because that's looking for where our list here, because we're printing out that list. And notice when it outputted the list, it printed from cantaloupe 3, bananas 2, apples 1. Because remember, when we add items to the list, it always adds to the start of the list. So if I wanted this to be 1, 2, 3, I'd have to actually add this item first. And then, of course, we see, hey, cantaloupe is on the list, but because now we've removed cantaloupe here with the deleting of the head node, you'll see it is not on the list. And then this while loop is deleting the head node, all right? And so that is going to, now you see start of the list. Of course, you'll see that it prints out that list, and there's nothing in here, so then we see end of list, because, again, we deleted out that head node, and so now that is no longer a thing.